Thank you, Regis. Now we'll move to the system engineering requirements part with Nick Kefalas.
Good morning. My name is Nick Kefalas. I'm the Senior Technical Officer for Sikorsky Aircraft Lockheed Martin. I'm also the certification lead for all systems and electrical equipment for our platform systems across the enterprise. Today we're going to talk about a topic that's probably not paid as enough attention as it needs to be in the industry, and that is how do we deal with system requirements in the development process of any of our projects. So what are requirements? Requirements are the starting point of any design, and clearly they weren't applied here as well as they should have been. Requirements are the starting point of any design in any system we have. Requirements are meant to basically, in the simplest of forms, define the definition of the design. And I know it sounds very simplistic to frame it like that, but it's true. We deal with two types of basic functions, what we call the intended function of what a system or a device is supposed to perform, and then the conditional behavior of what additional characteristics or abilities or operations that system is supposed to perform in terms of a system or subsystem functions. Requirements in general need to be function specific. They need to define what the device is intended to do. And clearly one of the biggest things we run into this industry is they need to be written in a way that they have to be verifiable. They need to be written with verification in mind. And it's not a typo that I have it there twice. It's intentional because 99% of all requirements we see right now in most of our system designs are not verifiable. They're written in a very generic and non-executable fashion. So one of the questions I get a lot from people is, why do we need to use requirements? Particularly also pertaining to systems that are either existing or are legacy in nature. It's a good question. The answer to that is we need requirements because requirements become the metrics by which a design is defined. If all requirements that we have written for a specific design are met, then we know that that device is actually going to function, its performance function as intended by the designer. The other important aspect to that is we needed to be able to demonstrate compliance to the aviation and safety regulations by which that design is meant to be. As tertiary function, it also provides the various technical folks, manufacturing folks, and engineers with a clear set of design characteristics and attributes to which they need to build that design. And lastly, it provides us with the basis for verification. So what types of system requirements do we actually have? And by all means, this is not a firm list. We can have 5 different system engineers up here, and they'll give you 10 different definitions of what system requirements are. But I've tried to distill this in what I believe is the most common ones. We have customer type requirements that are basically associated to the various type of aircraft functions, subsystems, based on what a customer needs are for the specific either device or system or subsystem. We have operational requirements that typically define functions as to what the device is supposed to do. How is it supposed to be operated? How are the crew and various interfaces supposed to interact with that device? We have performance-based requirements. That is what defines the system in making it useful. What performance or anticipated characteristic a device is supposed to meet. We have physical requirements such as dimensional, volumetric stuff. We have maintenance-based requirements that define how is that device supposed to function in terms of continued airworthiness, various types of day-to-day reliability and health monitoring. We have interfaces with regards to power and signals. How much power is a device supposed to consume? What's its thermal characteristics and such? And then we have stuff like certification, which I ironically put it last because most designers end up remembering certification at the very end instead of the very top of the process. So various regulations, safety, ADs, special condition papers. These are all very critical attributes that need to be thought of, not at the bottom, but at the top of the process. And lastly, and most importantly, safety. Currently, ARP 4754A and 4761 are the key elements to any design. It should be the starting point to any design we have. Performance constraints that are typically associated with the various safety applications or architectural constraints that a specific aircraft system or subsystem contains. And then overall is how do we put this whole thing together, right? Gathering all this stuff and making it into a coherent set of requirements that actually make sense to be able to be put together into some kind of structure is a critical aspect of the system requirement process. And then once we have all this, it's how do we get everything written down in paper? It's very critical to translate what we have in our minds and what we intend something to do, and then convey that in a clear, distinct fashion on paper. Writing about the functionality, writing what the intended function is and how that's going to convey to a designer, to a manufacturer, what you want that to do. Describing the function, describing that design. It's not an easy thing to do. And that's why I have this picture of a maze there, because it is a maze. It's a process that requires constant fine-tuning. There's no one-way trip here that if you start the process from beginning to end. It's a recursive event that you need to go back and revisit it so that you can meet the requirements of making everything distinct and clear. So once we have all these requirements, like I said, we have to bring them into something that makes sense. I typically tell a lot of my fellow engineers and various manufacturers that we deal with that a requirement set's supposed to be put together in a way that, God forbid, if we were to all die tomorrow, somebody could pick up that document and actually recreate the design without any other input from us. That would be a good set of requirements. Unfortunately, most designs today do not meet that criteria. You should be able to walk away from your requirements, and somebody else is supposed to be able to pick those up and recreate the device verbatim. That is a very difficult thing to do, and one that we still are struggling to do in a way that can be done consistently and repeatably. So what does a typical good decompositional function look like, or a set of requirements? And by all means, I'm not going to go into the details of how we get to this. We don't have a lot of time to do this. I typically spend hours and days when I teach my fellow engineers or at the university. But the intent of today is just to give you just a high-level set of what a good requirement decomposition should look like. It should be a top-down event starting with the aircraft function, safety functions, system architecture, any organic or inherent design requirements if you're a company and you want to reuse a specific function, circuit board, mechanical device. I call those typically organic requirements that would be up there. And they would be decomposed in this type of fashion where you would start with a high-level system requirement, breaking it down into the LRUs, into the subassembly board level, the circuit guards, and PLDs. I'm using an electrical example here because it actually provides the most easy structure to decompose top-down. And the most important thing that you should look at here is where every tier has two succinct sets of requirements. We have what we call either direct or allocated requirements, which are layered on the left side of the decomposition structure, and on the right side we have what we call the derived requirements. And we'll talk about this a little bit more as we go down. But this would be a typical decomposition structure for a electrical LRU system that we would use. Now, behind that, and this is, if I were to put one chart up for system requirements, it would be this one here, is the recursive nature of requirements verification, and design, and the intricacies associated with them. As I said previously, the process is a recursive process. You have to do this multiple times in order to get it correct. There's a relationship between your requirements, your verification conditions, and your design. And more importantly, there's actually attributes associated with how you assess these in terms of each other. And as you can see, there are feedback loops here, intentionally put there, in order to assure constantly, as you go through the life cycle development process of a device, that you constantly look back to make sure that both your design, your requirements, or your verification elements all play together. I had a professor once at MIT that once said it's the key to doing this thing, and his name was Steve Eppinger, by the way. Steve Eppinger said the key to doing this is keeping all three balls in the air at the same time. It is a very difficult task to balance all these in a way that they end up working together and not against each other. It's very easy to focus on one of these elements and then make the other two suffer. We see often over and over again where people focus too much on the requirements and then find out that those requirements are not verifiable or the design is not buildable. You can't produce that design. And vice versa. A lot of people focus on the design first and then try to backfill the requirement. That is probably the most common mistake we make in this industry. We think about this first, and then we try to fill in this and this later. And it just doesn't work. Your starting point should always be the requirement structure, and then you would have to look at the design, the verification, and then work backwards again to make sure that all three of these play together. As I said previously, once again, the structure for an electrical example that we're using here, or electronic example, is to take each phase of the design, your high-level system, your assembly level, your circuit card, your PLD level design, and break it into the key elements of each one, taking into account all the associated requirements that you have. Customer level requirements, internal or indigenous requirements, or organic requirements as I call them, performance, certification, and safety, and breaking them into the individual categories to make sure that your decomposition holds water at every tier. So what type of requirements do we typically look at? Again, this is just my view of the universe after 30 years of doing this. We typically deal with functional requirements, application requirements, implementation, input types, indirect requirements, what we call referred to requirements, global requirements, and derived requirements. So I'm going to quickly go over these for you on the next slide. Functional requirements. These are probably the easiest of all to understand. They're basically requirements that describe a function or a particular behavior. For example, an output responds to an input, or the device will do this if something else happens. Application requirements. These are the type of requirements that typically describe the how a particular piece of hardware or software is going to be used. Implementation requirements. Those are the ones that describe the aspects of the design or how that design is implemented. Input requirements, they express a descriptive or interface specification. We typically try not to use these because they're typically subjective in nature. Input requirements are very, very difficult to account for all possibilities, so we tend not to want to focus on these too much. Indirect requirements are requirements that just imply functionality from an indirect mean. Referred requirements are the ones that typically have external references to other systems or subsystems to which a specific element or design would interface to. Global requirements are those that have a response driven by an event, such as a group of events or a set of conditions that all have to occur for something to occur. And obviously, lastly, the derived requirements, which are typically offsprings or parent requirements that have higher level definitions. So how do we bring all this stuff together? Functions are, in the simplest of way, we try to break things in two categories. Simple systems that will use system-level requirements flowing directly to hardware or software, or complex systems, which are really the highly integrated ones that we mostly deal in these days, that have functions that are allocated to higher and then to lower level requirements. Most of the system that we deal in today's world are pretty much complex. I can assure you simple systems are very limited and very few part. As every year goes by, we see fewer and fewer of those. There's nothing out there right now that is not falling onto the complex system category. So how do we do a layout from a functional standpoint? Because it's important to actually look at it. And again, we'll take an electronic example here just because that's my primary focus in my career. We would typically start with a high-level device and then gather the requirements, those functional requirements, into specific sub-element groups. These don't reflect the actual circuit cards, nor should they, or the various categorizations of specific allocations to card or to circuitry. These should be done in a way that they're agnostic from allocating things to a specific device. Because once you start doing that, you're kind of leading the device in a specific direction, and that's not what you want to do. You want the design to flow from your requirements, not from your constraints. And that's a classic mistake we make a lot of times, is we will start designing something with the constraints in mind. We should never do that. You should approach your design from a purely hierarchical and organizational structure. Look where the functions and the requirements are driving you to, and then take into account the constraints. Starting the design process with the constraints first will only lead to disaster. You'll never get the design or optimize the design to where you want it to be. So a good way to approach this, is to grab the functional elements and then organize them in terms of how those functions relate to your various inputs and outputs, operational sides, functional sides, and again, without taking into physical constraints or organizational constraints. By doing this, you will then end up collecting the individual sublayer requirements under your specific functional elements, which then will allow you to make an assessment as to exactly what you need to do, how you want to organize them, and how you want to put these together in something that relates into either a circuit card, a firmware, a mechanical device, a subsystem, and then organize it that way. So what's a good way to approach writing these? This is another area where I believe we're still struggling as an industry to write good requirements. As a general thing, engineers hate to write, so that's probably the number one problem we have. But that aside, we always seem to forget how to write good requirements in the right level of detail. The number one guide has always been, we should always use requirements using the word shall. But to me, this is not an absolute. In the last 5-10 years, we've been seeing a lot of requirements that are being written in a way that shall is not always part of a requirement, but still is a requirement. So I think there's a big change in the industry and in the academic world as of late as to challenging this term that every requirement should begin with a shall. I think this is more of a legal issue or a contractual issue that's coming into the system engineering process than actually being part of the system engineering process itself. So while we do say you should use a shall, to me this is not always an absolute. I've seen many requirements as of late that do not contain the word shall and are still valid. So again, there's a paradigm shift starting to happen across this that may be in a little bit of a conflict with the legal community, but it's being worked out through slowly. Another good attribute as to writing requirements is to explain how the outputs respond to valid inputs or other triggering events. This is something that we really don't do well also. We don't seem to want to focus as to how we identify the operational aspect as to how an input will generate a specific output or a series of relational events will work. And when I mean how, I mean for every input. We always tend to focus just on the inputs that we care about, but the reality is we should be looking at the broader scope of how many possible real inputs are going to specifically affect a variable that will then lead to an outcome. It's very important to do this because otherwise you're actually predisposing your design to a win-win scenario rather than looking at the whole spectrum of possibilities that you can have. Make each requirement unique. I think that's kind of self-explanatory, right? We don't want to pile one sentence and make that contain 10 requirements, right? You want to break that up into something that's succinct. It's containing one requirement for every sentence or a function that you want to talk about. Assign unique identifiers to each requirements. I think most of us these days use doors as our way of capturing requirements, and if you don't, you probably should, because I don't know of any other tool that's actually better suited to this. The door system would actually assign a unique identifier called the PUI for you, so that's kind of done automatically. But if you're not using doors, make sure you always use a unique identifier. Be specific and concise in each requirement. Again, self-explanatory. Express requirements in terms of behavior. We kind of touched upon this already. Write it for a target audience, right? That's a very important thing here. You're not writing for your legal team. You're not writing for your contract team, even though a lot of times they do think you are. You're writing for your engineers. You're writing for your technicians. You're writing for the people that are going to actually build this. So write it from that perspective, assuming that this person is looking at this for the very first time. Don't make assumptions that, oh, he should be fully familiar about what quantum tunneling is. The guy may not know anything about quantum tunneling. You better be very specific and explain it to a level that an engineer or technician that's going to actually manufacture this understands specifically what you're talking about. Describe what is done and how it's done. It's another very important aspect. Be verbose. You need to be very detailed as to what exactly you want in your requirement. Always use the positive sense. Don't use shall nots or nots. I see a lot of requirements a lot of time where they're written in a negative sense. I don't understand why. But always write your requirements as a positive sense. And then use descriptions of outputs that can be observed and description of inputs that can be controlled. That's a very important one also. If your specific requirement is dependent on specific inputs or outputs, you need to be very descriptive about how and when those occur. Again, some general guidelines here. How can we improve our writing? I always believe you should use a format. If you don't use a format, you're going to lose control as to what you're trying to accomplish here. Every requirement should be written with a set of conditions. A typical template that I use is this here. Nothing proprietary or anything like that. It's pretty straightforward and intuitive. Typically have the function name, the definition of terminology, any trace links that are associated to this. Be very clear if it's a derived requirement or not. Describe its outputs, inputs, if there's any power-on behaviors, any reset responses, if there are any assertions that need to be identified, any de-assertions also, or any invalid behaviors. You don't have to fill these out. There may be more, but typically the important thing here is to use a format for each requirement that makes it concise. Why is this important again? If you're going to be working with a team, let's say, of 20 people, you need them to follow a format. Otherwise, each one of those people is going to use their own style of writing a requirement in. I've seen many programs where they've done a distributed set of the requirements, and when they got everything back, it was a jungle. Nobody knew what was going on. Why? Because they never followed a standard format. Very important, especially if you're working with multiple people across multiple platforms. So what are some general considerations, again, when you do this thing, right? And I'll start from the bottom up here. Requirements can have allocation and decompositions that can go down through one or more levels of abstraction. What does that mean? That means that you got to be careful when you write requirements to the level of detail you're writing them. I see a lot of people write requirements, a lot of companies write requirements, and on the very top of your decomposition structure, at the very top, like even at aircraft level or subsystem level, they put so much detail that when you try to decompose those requirements down, there's nothing left. The requirements are already written in such detail at the highest possible level that the only recourse somebody has is to just continue to copy that requirement down in the tiers. First of all, that's a bad indication of a system engineering effort. It's also a bad sign that your engineers are not creating the requirement at the highest level possible, which means that you are missing out on derived requirements, allocations, or other relationships because somebody has already predefined it to the umpteenth level. A good example of this is I've seen at the aircraft level definitions where they will say the impedance of the input of this device shall be 100 ohms. That is not the place to be defining 100 ohms. That's not the place to even be talking about any resistor values. That kind of detailed information should be several tiers down. And if you see that level of detail at the highest level, you know your decomposition structure has problems. Another important one to look at is system requirements that capture the functionality and additional requirements from the safety process, right? This is so important, and it's one of the top level requirements that you should do. Safety should be driving you from the very beginning. You should be intimately knowledgeable with your functional hazard assessment and system safety assessment for the device or the particular system you're doing. Why? Because system safety is going to affect the way you write your requirements. So they have to be right there on top. You need to be familiar with what your functional hazard assessment is, any system safety assessments or PSSAs that you may have, and they need to be flowed down at the top. The mistake a lot of companies do is they wait till they complete the whole requirement decomposition structure and then somebody says, oh, I got to go look at the safety now. That is absolutely too late at that point. Your system safety process should be running from the top in parallel. If you remember several slides back, I had the system safety process right at the top because that is the place it should start. It should not be an afterthought. It shouldn't be oh, by the way, I think I have to do this whole thing to DAL A. And you remember it after you've decomposed your whole structure. It is way too late to do that at that point. So keep that in mind. You want to start that at the very beginning of the process. The design can show how requirements are decomposed. Very important. I love this because this kind of captures everything. Don't have a preconceived notion as to what your design is going to be. Let the process flow it out for you. That's a very important constraint, and it's almost like a paradigm shift to get us to move away from predetermining what your design requirements are going to look like. You got to let the process flow out. Why? Because you may discover things that you never knew. You may discover things that, you know what? My assumptions were completely wrong. I shouldn't do it this way. The process is so important to kind of guide you through what you should do and not do that you need to allow it to flow out. There's a reason why we have a system decomposition process like that, because the benefits are, as you go through your life cycle development process, you're actually going to let the process come back to you and provide you the feedback necessary to make the necessary corrections, or even decide that, you know what, I'm designing this whole thing wrong. I should go back and do it a different way. But Many a times, we don't do that. We kind of predetermine what the design should be rather than what the design needs to be. So, very big difference there. PLD requirements, and this also applies for software, not just for programmable logic devices. So we can phrase it as firmware and software requirements can be allocated and decomposed from the requirements for the various circuit or software that hosts either the software or the device. So what does that mean? At the very lowest level is a lot of folks try to fit, both for the software side and the firmware side, things within the confines of the device limitation. Again, it's a predetermination of where you want to go, but you need to let the process work itself out. Aircraft level requirements should be and can be allocated to various systems, pretty self-explanatory. System design should capture the features and architectures necessary for implementing system functionality, safety, and reliability, right? We just talked about that. Software requirements can be allocated and decomposed from the requirements to the circuit card that hosts it. This is kind of similar to the firmware one. And then each level of abstraction, this is very important, can repeat its allocated requirements until there is a design. What does this mean? You may find yourself for similar inputs or similar behaviors generating similar requirements, but they may be falling under different functionality trees. What that means is don't panic when you see that happening. That, again, is part of the process that feeds back to you to provide you some visibility as to what's going on. So if you see the same requirements or the same level of abstraction decomposing, it's not a bad thing, because you may have similar I/O that may be residing on multiple cards, or needs to reside on multiple cards, or needs to be expanded to various other platforms. So it's not a bad thing to see that. It's just part of the process. So let's talk a little bit about verification. I've got to keep my time on time. You'll let me know, right? Verification. As we said before, we should be writing requirements with verification in mind. It's a big problem where I see requirements that actually don't have any verification capability. They're written in such a high level that verification becomes almost impossible. Or the verification they choose to use is almost childish in a way, because you're not really getting any benefit or any feedback as to how well your design is performing. So you always want to write requirements again to a level that allows them to be verifiable at the lowest level possible. I say that a lot because if you've done your decomposition correctly, you should be able to verify at the lowest level repeatably. Now, I'm not saying there are not going to be requirements at some level that you're going to not be able to verify and that you'll have to move up to the next highest level. That's allowable, but your goal is to be able to test at the lowest level possible, and you should always approach it from that standpoint. So what type of verification activities do we typically do in any design? We typically do inspection, analysis, simulation, and test. Inspection typically is verifying either the design through drawings or through timing charts or diagrams like that. Analysis is pretty self-explanatory. Simulation, also explanatory. There are various types of simulation tests that we do, and then the actual tests, either on the device itself or through the aircraft testing. So here's an example of what we would do in terms of verification from a life cycle development. Again, as the decomposition structure comes down, as I said before, we want to try and verify at every tier of the process. You want to make sure that at the hardware level, at the board level, at the PLD level, that you have coverage at every phase of the process. It is very important to do that, to assure that you have proper coverage. The sum of all the testing that you do should add up to provide coverage to the entire set of requirements for your design. You should never ever try and test the highest level. That's another mistake that we do in the industry pretty consistently. We write requirements, we decompose them, then we figure out, oh, I can't test anything at the low level. And we try to do one big ATP at the box level and then call it the day's done. That is absolutely bad coverage. So we should always strive to test at the lowest level possible. Why? Because as you're moving up from the lowest level to the highest level, you're actually going to see gaps or issues in your design materialize. And then you can determine what of those results are pertinent to the design, which ones need to be fixed, which ones are not really realistic, and then see if your design needs additional improvement or your requirements need additional improvement. Don't forget that you may see through your test process that some of your requirements may not be as mature or correct as you need them to be. So even the test phase, if you remember the 3 bubbles earlier, that also drives both design and verification. We'll kind of skip a little bit just to save time here. Am I almost done? So let me just go straight to we'll close with this one here because this kind of brings everything home. As I said earlier, these are where we want to be, the 3 elements: requirements, design, and verification. The idea here is if all of these are all balanced and the level of testing is correctly done, you will be able to confirm your design. And as I said before, if you find errors in your test process and you've set it up correctly, you'll be able to know if your design needs tweaking, if your requirement needs tweaking, or your verification needs tweaking, because all 3 of these need to be playing together. And the only way you're going to be able to do this is if you have set up your requirement decompositions correctly from the beginning. Thank you very much.